Hey, so in this video, we're going to be talking about these 10 alkene reactions and their intricacies, how to solve them right for every single problem, and how to approach these step by step. So let's just jump right in, and we'll come back to this web and answer this question for all of these at the end of the video. So let's remind ourselves that an alkene is simply organic structure that has a carbon-carbon double bond. And that carbon-carbon double bond is actually quite reactive thing, right? So we have these electrons. Remember, bonds contain electrons. In this case, we have a double bond. That double bond has pi electrons that can freely act as a nucleophile for our reactions. So oftentimes, because of this pi bond is electron rich, we're able to react this with a certain number of electrophiles. Oftentimes, what's going to happen with these reactions is that, notice that there's two carbons on our structure. We will have a molecule that adds two groups off of those two carbons of our double bond. So for example, we'll have some A and some B. And that A and B, which we will represent as two different groups, will be added somehow off of our structures. So I could add A off of the place of one of my double bonds, or one of the carbons of my double bonds. And then I can add maybe B off the place of another one of the carbons of my double bond. Now, this is a very simple explanation. I'm just deleting these dots. This is a very simple explanation of what is a very complex, well, not complex, but there's more questions that we have to ask ourselves. So let's just delve into those questions. The first question is, what are A and B? Because, right, we can be given a number of reactants that can react with this nucleophile. And the question oftentimes is, first, what am I adding? What are A and B? We'll delve into this question with some examples in just a second, but that's one of the questions we need to ask. The second question we need to ask is, well, where do A and B go? Not necessarily. I know that A and B are going to go off of the carbons of my double bond, but in this case, I just chose to put A on the left carbon and B on the right carbon. I could have also chosen to put B on the left carbon and A on the right carbon, right? So the way that I suggest thinking about this question is not left, right, up, down, right. Instead is, does A or B go on the most substituted carbon? And I like to abbreviate substituted as just sub carbon. What do I mean by the most substituted carbon? Well, let's look at the double bond and the carbons that we're investigating. So these two carbons. This left carbon has 1, 2, 3 carbons attached to it. So this is a tertiary carbon. The right carbon has 1, 2 groups attached to it. It is a secondary carbon. And so our most substituted carbon in this case is going to be our tertiary carbon. And so notice that for the products, A got added on the tertiary carbon on the left product, but B got added on the most substituted tertiary carbon in the right product. So this is the question that we're asking. Does A or B go on the most substituted carbon? 3, the third thing you should ask yourself do we do a syn or addition? I hope you remember from the conformations and our Newman projections, chairs, things of this nature, that groups can be on the same side of a molecule or on opposite sides of the molecule. We usually represent syn as something like this, syn as in same, where both of the groups are on the same side. I've arbitrarily chosen to put both A and B on wedges, but it could be the case that A and B are both on dashes. Sin just means that they both need to be on the same thing, whether it's wedge or dash. Anti, on the other hand, we have A and B. Anti means that they need to be on opposite sides of the molecule. So if one group is on a wedge, the other group needs to be on the dash, and vice versa. Right, so this is the anti addition. Right, and again, I've arbitrarily chosen these, but if we have an anti addition, we can get both sets. So we can get both this set and this set where A is on the dash and B is on the wedge. The same thing is true for sin. Finally, the last question that you need to keep in mind is, do I do carbocation rearrangement? Again, I'm lazy, so I use this squiggly R as my way of saying carbocation rearrangement. But these are the 4 questions that we need to ask ourselves in order to begin understanding how to solve these problems. So the best way to learn these reactions is simply through practice. And so let us get some practice down. This first reaction here is hydrohalogenation. I know that because I'm adding hydrogen and a halogen. There is a hydrogen and a halogen. So this reaction, I guess I can write this down. Hydrohalogenation is when I have an alkene and some HX. So when I'm reacting an alkene with some HX, where X can be chlorine, bromine, iodine, etc. And there are a couple of things that I need to do. In this case, I'm going to, for all hydrohalogenations, I'm going to add H and X. So for example, in this first case, I'm going to add H and Cl, right? The next question that we should ask ourselves is, does A or B, does hydrogen or the halogen go on the most substituted carbon? This follows the Markovnikov rule, spelled Markovnikov with a capital M. It's someone's name. Markovnikov rule. And that just simply means that we're going to place the halogen, so the non-hydrogen atom, the halogen, on the most substituted carbon. So we have an option between a tertiary carbon and a secondary carbon of our double bond. We're going to choose the tertiary carbon of our double bond because that is the most substituted carbon. We'll place the halogen there, and consequently we'll place the hydrogen on the least substituted. This reaction will do syn and anti addition, and indeed there is carbocation rearrangement. So 2 things that you might be wondering. First of all, the H and X part, you probably understand why we're adding H and X. But for Markovnikov, syn and anti, and rearrangement, you might be asking, how do you know that? And the answer is that the mechanism tells us. So I suggest getting very comfortable with the mechanism. I will have probably resources available about the mechanisms of this reaction soon. But as for now, make sure you really understand the mechanism to understand why we get Markovnikov addition. Why do we end up with syn and anti addition? Why do we have rearrangement? Okay. So if we can answer these questions, which now we have answered these questions for hydrohalogenation, we can do this for every single hydrohalogenation reaction we see. So now let us look at our first reaction. We have 2 carbons, right? These are the 2 carbons that I can work with. And off of those 2 carbons, I need to add hydrogen and chlorine, right? That's the first step, to add hydrogen and chlorine. So I can add maybe my hydrogen here, my chlorine here. But I know I need to do this Markovnikov style. So I need to figure out which of the carbons are most substituted. Again, I have these 2 carbons. This leftmost carbon it has 2 carbons attached to it. So this one's secondary. This rightmost carbon has 2 carbons attached to it. It is also secondary. Because both of those carbons are secondary carbons, it's not going to matter where I put the hydrogen or the chlorine. In fact, I'll get the same product. This also tells me that, so let's just actually do that first step. I can add my hydrogen and my chlorine here. And in fact, it would be the exact same thing to draw my chlorine and my hydrogen here. These would be the exact same product. Right now, all I have to do is rotate the molecule. You can also figure this out by naming it. If you named both of these molecules, you still get 2-chlorobutane, right? So they are identical. You don't have to draw the same thing twice. What else don't you have to draw? Well, I don't have to draw carbon-hydrogen bonds, so I don't need this. And voila, I've added hydrogen and I've added chlorine. The chlorine on the most substituted side, but again, there's no most substituted side. The last thing I need to check for is, do I have a chiral center that I formed? These are the 2 carbons in which I added a new group. On the left carbon, this is not chiral because it doesn't have 4 different groups, right? It has 2 hydrogens off of it. The rightmost carbon, does it have 4 different groups? Well, it has a chlorine, a hydrogen, a methyl group, and an ethyl group. These are 4 different groups. And so this is a chiral center. That means that we should probably indicate using wedges and dashes. This, I'm going to arbitrarily put the chlorine on a wedge, but I could also have arbitrarily put the chlorine on a dash. So I can have this plus its enantiomer. You can draw this, or you could actually draw the enantiomer. Both are fine options. So we didn't really see the application of syn and anti or rearrangement yet. Nor did we get to see Markovnikov. So let's see if the next example will help us see this. So this example, we have these 2 carbons, right? These are the carbons of my double bond. The top, I have a tertiary carbon. The bottom is secondary, right? So these are the substitutions of those carbons. I know that again is because this has 3 carbons attached. This only has 2 carbons attached. And I'm going to add H and X. In this case, X is Br, so I'm going to add H and Br. I'm going to do so in a Markovnikov fashion. So I'm going to add the Br on the most substituted side. So let me do that. The most substituted side is the tertiary side. I'll add my Br on the most substituted side. Add my Br here. And I also have hydrogen on the least substituted side of that double bond. Wow, we've gotten this far. Now, the next thing I need to do is figure out, I don't need to draw in carbon-hydrogen bonds, so I can get rid of that. Now, the next question is, do I have a chiral center? And this one's a bit tricky for a lot of students, so let's take our time through it. Do I have a new chiral center? Well, I have a bromine, one of my groups. I have a methyl group for another one of my groups. And I know those 2 things are different. So for now, I can actually just ignore them. And my way for ignoring them is going to be, maybe I can just cross them out temporarily. I'm just going to ignore this. Now at the center where I'm still questioning the chirality. So this is the center, the carbon center in which I'm still questioning the chirality. I can draw a plane of symmetry and ask myself, are both sides of that ring equivalent? And they are, right? The left side, there's no difference between this top side of the ring and this bottom side of the ring. And so indeed, this is an achiral atom because those two groups are identical, right? And we need to have 4 different groups for something to be chiral. So this is achiral. And as a consequence, I don't need to draw plus and enantiomer. In fact, I don't even need to draw wedges and dashes here. This is sufficient. Let's do the next question. So the next question, again, has 2 carbons, the rightmost being secondary, the leftmost being primary. And I can, again, add hydrogen and a halogen. I can do so in a Markovnikov fashion, syn and anti. One thing I have not talked about yet is this rearrangement piece. And here the rearrangement is going to be important. Rearrangement occurs whenever, let's actually go through the process. So the first thing we need to do is, instead of placing our Br, earlier we just placed the Cl off of the most substituted carbon, or the Br off of the most substituted carbon. Instead of doing that, let's instead place a positive charge off the more substituted carbon. The reason why we're doing that is because this is a key intermediate within the hydrohalogenation mechanism. So I'm going to place a positive charge off of my more substituted carbon. Again, the mechanism will explain why we do this, but for now, trust me. The next thing we're going to do is figure out the substitution of our carbocation. And then we're going to figure out the substitution of its neighbors. So to the right, I have a tertiary carbocation. To the left, I have a primary carbocation. Finally, I'm going to ask myself, are any of my neighbors, do my neighbors have a more substituted carbon? And particularly, not only that, but will me doing rearrangement give me a more substituted carbon? So I can rearrange to only my neighbors, not over here or here. We're just going to do 1, 2 shifts for the purposes of this class. And we can, so we'll look at our neighbors just like we did in this procedure earlier. And we say that, okay, indeed, I have a tertiary carbon that is more stable than my secondary carbon. So I can do rearrangement. Rearrangement arrows, if you want to draw them, they look something like this. This is a hydride SIF, so I need to draw in a hydrogen. And I need to place that hydrogen onto that positive charge. I need to move that hydrogen to that carbon with that positive charge. As a consequence, I end up putting that hydrogen off of this carbon and a positive charge off of that carbon, which does indeed form a more stable carbocation. I started off with a secondary carbocation. I'm ending with a tertiary carbocation. And this is the procedure for rearrangement anytime you have to do it, whether it's this mechanism, SM1, E1, etc. Because I am with the more stable carbocation, this is going to be where I add my nucleophile. And I add my nucleophile off of that positive charge. You should never, ever, ever draw a positive charge in a final product. There will be very, very, very few cases, if any at all, in your organic 1 and 2 life where you'll ever have to do that. So we'll just add in the box with that asks you for your product, you'll add your iodine in the position of that positive charge. So this is the carbon of that positive charge. This is the carbon that we add the iodine off of. Finally, I had to ask myself, did I form a chiral center? Did I form a chiral center? Let's see. Well, this is probably the carbon that you're questioning if it's chiral. And let's look at if it has 4 different groups. This has a methyl group, an iodine, another methyl group, right? Because we have 2 methyl groups, this is not chiral. So it's okay to leave without wedges and dashes. Finally, let's look at this last question down here. We have a tertiary, I don't know where mine's going out of place. This is a secondary carbon and a primary carbon. The question is, well, we need to add hydrogen and a halogen. But before we do that, we've seen that we can do carbocation rearrangement. Let us check to see if we can do carbocation rearrangement here. We can draw in our structure really quickly where we put the positive charge on the most substituted carbon. On that most substituted carbon, I find that it is secondary, and I look only at my neighbors, so only to the left and to the right here. Because the carbon to the left has a higher substitution, this carbon, we're going to do carbocation rearrangement, and also because this is a mechanism, I don't have to show me drawing in that hydrogen and moving it. I can just simply move. I can simply just move my positive charge. Finally, I did indeed form a more stable carbocation, so I know I've done this right. And then I can add my chlorine off of the position. So let's do such. We can add your chlorine off of that tertiary position. Finally, like we've done for all these questions, we can ask ourselves, did we form a new chiral center? This is the one that you're probably questioning. We don't have to worry about this because this never participated in the reaction, right? So remember, your mechanism can help you see this, but also notice that we never ever moved our carbocation there. The reaction never happened there. So we're only going to look at this carbon. And notice that that carbon is indeed chiral. It has a chlorine, it has an ethyl group. And again, since we know those two are different, we can simply ignore them for the rest of this exercise to see if the other two groups are different. The top part of this molecule is different from the bottom part of this molecule. And so this indeed is a chiral center. And because it's a chiral center, what instead we'll do, instead of putting them on just these sticks, unless your teacher allows you to, some teachers do, but just to be universal, I know most teachers allow this. You can put one on a wedge, the other on a dash. And then in this case, I can't say plus enantiomer because plus enantiomer will flip all of my chiral centers, right? And I don't want this chiral center to be flipped because that chiral center never participates in the reaction. So I'll just draw in the other product. I'll get the diastereomer. Oops. And this here is how you can do hydrohalogenation. Notice that the syn and anti, it does matter. This matters when we end up forming multiple chiral centers, and we'll see an example of this very shortly. So what if I wanted to place bromine on the least substituted carbon? Again, remember from our last examples, we've always placed bromine on the more substituted side of our alkene. So what if we wanted to do it on the least substituted side of the alkene? Well, we have a different reagent. In fact, we have just additional reagents that we need to add here. This is going to be a peroxide. We represent this as ROOR. You could also see it as R2O2, right? These mean the same thing. Light, sometimes written as HNU, or heat, sometimes written as delta. So the light or heat are the initiation part of the peroxide, and HBr is what's added across our double bond. But notice that in this case, well, this is not true. This is not correct for this reaction. Rather, what happens is we place our Br on the least substituted carbon. So we'll place it here off of this least substituted carbon. So how does change our list? Well, we have Antimarkovnikov Hydrohalogenation, Markovnikov hydrohalogenation. We still are going to add H in the halogen, but instead, again, it's going to be Antimarkovnikov. So we should remember that we have Antimarkovnikov when we have the conditions of peroxides. This means that instead of placing X on the more substituted side, we're going to place our halogen on less substituted side. This still does give the syn an anti-product. And this, because it never goes through a carbocation intermediate, is not a candidate for carbocation rearrangement. So oftentimes, for the rest of this video, I'll probably just not write no rearrangement unless I'm trying to emphasize that point. But this, I guess I can write it here. This reaction does no rearrangement. One other thing is I've left this product like this, but let's consider if there's chirality and if we need to draw wedges and dashes. So looking at the 2 carbons at which we added our substituents, let's see if those 2 carbons are chiral in our product. I find that I have for this purple indicated carbon, I have 4 different groups. I have a hydrogen and methyl group, and the 2 sides of the ring are different. So this is going to be, I could place this, for example, on a wedge. And because we can get syn and anti products, what we need to do is make sure that that hydrogen and that bromine are always, they can be both, right? So let's say if I place my bromine on a wedge, and I place the hydrogen that I added on the dash, because what matters is the hydrogen and the bromine being syn, right, or anti. In this case, notice that these are anti. I have one thing on a wedge and one thing on a dash. So this is the anti-product. And I could have gotten the enantiomer, right? I didn't have to place the bromine on the wedge and the hydrogen on the dash. I could have done the opposite. So I could have also gotten this product. Let's make sure we draw it correctly. Where this is the enantiomer of these 2 things are enantiomers. But again, these are just the anti-products. I could have also gotten the syn products. So I could have gotten the case where I had the bromine and the hydrogen on the same side. So let's look at the case where the bromine and the hydrogen are on the same side. Well, that's a Br and a hydrogen both on a wedge. And that methyl group would be on a dash as a result. But I don't have to stop here, right? I arbitrarily place the bromine and the hydrogen on a wedge. I could arbitrarily place the bromine and the hydrogen on a dash. Right, so let's move you over. And we can do that. We can place, and I'm running out of room, we can place the hydrogen and the bromine on a dash. Upon inspection, these are not none of these products are the same. These 2 are enantiomers of each other. And as a consequence, we can say that we form 4 different products for this reaction. So this is that reaction in its entirety. Let's do another example. So this next example, I can choose to put my bromine on either the secondary or the primary carbon, but because this is in peroxide conditions, light or heat, maybe I can write this for the next one as well, just so that we don't have to think about it. Because this is in peroxide conditions, I can choose to put my bromine on the primary or the secondary carbon. Let us put the bromine on the primary carbon, right? Because this is an anti-Markovnikov reaction. I have to place my halogen on the less substituted side. So let's do that. So So I place the Br off of the less substituted side. I place a hydrogen here, but again, you don't have to draw in that hydrogen, so we'll just leave it there. Did I form any chiral centers? Let's look at the 2 carbons at which I did my reaction. The leftmost carbon here has 2 hydrogens. It is not chiral. The rightmost carbon, it also has 2 hydrogens. It is not chiral. So this is the product. This is what you draw. Finally, for this last one, we have the secondary and the primary carbon. We're going to choose the primary carbon because, again, the primary carbon is the less substituted side to put our bromine on. So we will put our bromine on that carbon. Let's just go ahead and add the bromine off of that carbon. And notice this here is the rest of the molecule. It does not participate in the reaction. Because it does not participate in the reaction, leave it alone. Just leave it alone and keep it exactly as it was drawn. Finally, let's check the 2 carbons that we added something off of to see if they're chiral. This leftmost carbon is not chiral because it has 2 hydrogens. This rightmost carbon is not chiral because it has 2 hydrogens. So the next reaction we'll talk about is halogenation of alkenes. Halogenation of alkenes. I'm doing this in this order because halogenation of alkenes. I'm doing this in this order because these are the most common reactions that you'll find in an organic chemistry textbook or an organic chemistry class. So let's go ahead and get started. Halogenation of alkenes, we're going to add our 2 halogens. Those are the 2 things we're going to add. The second question we asked ourselves are which one of these groups are going to go on the most substituted carbon, and it doesn't matter. Right? It doesn't matter whether or not chlorine or another chlorine goes on the more substituted side. So this is X2, by the way. It doesn't matter if chlorine or chlorine goes on the more substituted side. So I will just leave this place blank. Will this be a syn or anti-addition? I'm not sure if you remember, but we have these chloronium or bromonium intermediates in the halogenation of alkene mechanism, whereby we can only react on one we have to do a backside attack on the 3-membered ring. So this reaction is an anti-reaction. And because we don't form a carbocation in the process, we cannot do rearrangement. So this reaction is quite simple. All we do is on these 2 double bonds. Fortunately, we don't have to even consider rearrangement, so it's always going to be off of the double bond. Off of that double bond, we are going to add chlorine and chlorine and make sure that they're on opposite sides. So chlorine and chlorine. Notice that I added 1 chlorine on a wedge and the other chlorine on a dash, and they are coming off of the positions of our alkene. Right? One's coming off of one of the carbons, the other's coming off of the other. This is it. That's all. Reaction done. Actually, I should say I randomly chose this chlorine to be on a dash and this chlorine to be on a wedge, but I could have chosen the opposite. So in this case, we could also get it's an enantiomer. Again, you can draw this out or you can put plus EM. The bromine reaction, and also just in case you're curious, you could also see Br2 from Gen Chem. Hopefully you remember. You can also see this right now as Br, same thing as Br2. Right, so I can add the bromine and the bromine off of both sides of my double bond. Right, they have to go off of those 2 carbons. Do not place them anywhere else. Where I have 1 bromine here and 1 bromine on the dash, so 1 on the wedge and 1 on the dash. Now remember, and this is a mistake students commonly make, you need to make sure that you have all of your carbons. Carbons cannot disappear, conservation of mass. So we started off with 1, 2, 3, 4, 5, 6, 7 carbons. I should end up with 7 carbons. Right now I only have 1, 2, 3, 4, 5 carbons in my structure. So 6 and 7 must still be there. Since on the bottom carbon off of 5, since we already have one group on a dash, I'll put that methyl group number 6 on the wedge. And because on carbon 1 I have the bromine on a wedge, I'll put that methyl group on a dash. Now again, I've arbitrarily chosen one of those bromines to be on the wedge, the other bromine to be on the dash, so I can get the enantiomer. Finally, for this last question, scroll down a bit. I have, I'm going to do the exact same procedure. I have 2 parts of my double bond. I can add 1 chlorine off of one of those carbons, another chlorine off of another one of those carbons. So I end up adding 1 chlorine. Again, I can make one a wedge, arbitrarily, of course, and the other a dash, arbitrarily, of course. And I won't forget this methyl group. Now you might be tempted to just put plus E in here, but if I did put plus E in here, that means the enantiomer of this molecule, meaning that this wedge becomes a dash, this wedge becomes a dash, this dash becomes a wedge if you keep the molecule in the same orientation where this ethyl group is furthest to the left. And that's not what I want to say. What I want to say is that only these 2 flip, because only these 2 participate in the reaction. So instead of writing plus enantiomer, I should be specific with the diastereomer that I get this diastereomer. These are the most of it, I think, advanced that these questions might get. Quite frankly, for an intro class, they might not jar your brain this far, but you should keep this in mind, right? The only restriction that I have is that I need to add 2 chlorines off of my double bond, and that they need to be anti. So in this case, I've added my 2 chlorines off of my double bond, and they are anti. Let's do hydrogenation. So hydrogenation is whenever we add 2 hydrogens, which is indicative of our reagents, right? 2 hydrogens, right? 2 hydrogens down here. These are hydrogenation reactions. Hydrogenation. And yes, typically they happen with H₂ and palladium, platinum, or nickel, sometimes written with this not symbol. And yeah, quite frankly, these are almost the easiest reactions. What we're going to do is we're going to add H and H. Again, because they're both H's, it's not going to matter where they added. There's no like Markovnikov or Antimarkovnikov here. We have, what else is important? Well, this reaction is the syn addition. Again, the mechanism can help you explain that. And no rearrangement is possible. And so for this particular reaction, let's move these over. What we're going to do is we're going to add H and H to our carbon-carbon double bonds. Remember, this is a reaction of alkenes. So this is a carbon-oxygen double bond. We'll leave it alone. But for this carbon-carbon double bond, we will add 2 hydrogens, and we'll add them syn to each other. So we end up with, and I guess I don't have to draw it this way. We end up with these 2 hydrogens being added on the same side. And usually we don't like to draw this hydrogen with these small angles, like these small angles between things. So oftentimes we'll flip that carbon down so that we can maximize the repulsion. Remember Vesper theory from the early parts of this class. But if you draw it that way, you probably will be fine. This is us adding 2 hydrogens off of that double bond. Now, those are in the syn manner. I could have also put them both on wedges and dashes. But even the question before that is, are these chiral centers? Well, let's look at this one. You might be deceived in thinking that it's chiral centers, but what are the groups coming off of it? Well, I have a hydrogen, and I have another hydrogen, right? Carbon must have 4 bonds. I have 2 hydrogens coming off. This is not chiral, so it doesn't need wedges or dashes. In fact, I can draw this as just a line. Same thing with this one. This is not a chiral center. It has 2 hydrogens coming off, so I can draw that as just a line. And in fact, I don't even have to draw in carbon-hydrogen bonds, right? So I don't even need any of this. I could have just drawn this. Or again, single bonds can freely rotate, so I could just draw this, and this is fine. All right, so look what I've done. I did all of that fancy discussion because we have to do that at the beginning when we're teaching this. But really, look what's happened. We've had a double bond, and we no longer have a double bond. That's it. That is, most of the times, that's all we'll do. There's sometimes we'll get more complicated questions, but I think these next two are as complicated as they can get. All right, so in this case, I have H2 and PD. I have a double bond. And again, I'm going to add my 2 hydrogens. I have to add them in a syn fashion, though. So I will do that. Let's say I want to add both of them on dashes. So I add those 2 hydrogens on dashes. That means that my methyl groups are both going to be added on wedges. And I don't need my bonds to hydrogen. I don't need to draw in my bonds from carbon to hydrogen, so I can draw this. I arbitrarily chose to put those hydrogens on dashes, but I could have also chose to put those hydrogens on wedges, meaning that I get the enantiomer as well. And that's that. I know that these centers are both chiral. I think you guys can see this is a chiral center and this is a chiral center. Now let us do this one with the nickel catalyst. Again, as you probably note, we're just going to add our hydrogens on both of the same side. When we added those hydrogens both on the same side, again, we put the other groups on the opposite side. So if I added both of my hydrogens on dashes here, I added both of my wedges, or both of my methyl groups on wedges. So I end up with that. And do I get the enantiomer here? Question mark. Let's look. Well, this center is indeed chiral. It has 4 different groups. This center is also chiral. It has 4 different groups. But there's one other thing we can notice about this molecule that we haven't seen before, and it's that there is a line of symmetry, which means that this is a meso compound. And the quote enantiomer of this compound, it's quote enantiomer. It doesn't actually have one. But if we say quote enantiomer, where we just flip those wedges and dashes, is the exact same compound. These 2 compounds are the exact same because of that internal plane of symmetry. So if I simply rotate this molecule around, I'd find that those 2 molecules were exactly the same. And so I wouldn't put plus enantiomer in this case, but this is less can you do the hydrogenation reaction at this point and more of do you remember your stereochemistry. So next we're going to talk about our hydration reagents, which add, well, as you probably can guess, H and OH, water. And so these are, all of these, I guess all are hydration reagents. And what else? Each of them have different names. So this top one is called, this reaction is called acid, maybe I'll put it on the side, it's called acid-catalyzed hydration. The next one is called Oxymercuration, which is the name for the first step. Notice it has 2 steps. The first step is oxymercuration, hyphen with no space between them, but I just ran out of space, so I'll put a new line. Oxymercuration-Demercuration. The last one is called Hydroboration, which is the name of the first step, and then oxidation. This is the name of the second step. So these are their names, if you want to look up more about these reactions. But with these conditions, they all add H and OH. Each of these reactions add H and OH. They're hydration reagents. So anytime you see any of these, you're going to add H and OH. But the question is, well, if they all add H and OH, why do we need 3 different reagents? Well, that's because they can add H and OH differently. So, for example, off of the more substituted carbon or the less substituting carbon, they can add them. Some of them can do rearrangement, some of them cannot. Some of them can have anti and syn, so we'll talk about that. Again, all of these answers are explained by their mechanisms, but let us just talk about how to predict the products. For acid-catalyzed hydration, this goes through a carbocation intermediate. And that means that this reaction, number 1, is going to be a Markovnikov reaction where we add the OH on the more substituted side. So this OH is going to be added to the more substituted side. Again, because it goes through a carbocation intermediate, it has rearrangement. And again, because of the carbocation intermediate, this can add syn and anti. The Oxymercuration-Demercuration does not go through a carbocation intermediate, but it still is a Markovnikov addition. So if we look at the difference between acid-catalyzed hydration and oxymercuration-demercuration, right now they look very similar. But the difference is that our oxymercuration-demercuration reagent cannot do rearrangement. Usually these are going to add anti each other. So the H and the OH will be anti each other. And then finally, the Hydroboration-Oxidation. This is our anti-Markovnikov reaction. I like to memorize that this one is an anti-Markovnikov reaction by remembering BAM. So notice it starts with a B. So this is boron. Anti-Markovnikov, also known as BAM. And this reminds me that, okay, out of my hydration reagents, this is the only one that will add anti-Markovnikov. So I remember BAM. Hopefully that's helpful. But if not, obviously, feel free to use whatever things that are helpful for you. I think this is a little bit intuitive, but just to write it down explicitly, because it's an anti-Markovnikov reaction, it's not going to do rearrangement. If, for example, I added a positive charge, this reaction doesn't go through a positive charge at all, but this is just a thought experiment. If I did an anti-Markovnikov reaction, but I had rearrangement, that means I'd add my positive charge here. And of course, it would rearrange to the more substituted carbon. So again, Hydroboration-Oxidation does not even have a carbocation, so it couldn't do a rearrangement. But any anti-Markovnikov reaction is not going to do rearrangement, because if it did, it would defeat the entire purpose of anti-Markovnikov. And this is going to do a syn addition. Okay, so these are, I would make a flashcard of this. I actually literally have a flashcard probably of this exact question when I was studying organic chemistry, because this one is not very complex. It's not really hard, but you just have to, see it a couple of times and make sure that you understand the tiny nuances between each of them, because they do add H and OH. Another way you can remember that these are hydration reagents is, again, the reagents kind of give it to you. So this is H₂O, H and OH. This also says H₂O, H and OH. This doesn't have H₂O anywhere, but you can remember BAM, or you can just remember when you see these borons, they mean hydration reagents. Okay, so let's do the bottom two, because they don't do rearrangement, and we love reactions that don't do rearrangement, at least on paper, and actually in practice too. So let us do that. In this case, we simply have to add H and OH off of either one of these carbons. Because this reaction is a Markovnikov reaction, we're going to add the OH off of the more substituted carbon. So this was the secondary, this was the primary. We're going to add the OH off of the secondary carbon. Because this secondary carbon is a chiral center, it has 4 different groups. It has the OH, the hydrogen, the methyl group, and the tert-butyl group, right? I can say this is on both a wedge and a dash. I can do the exact same thing for this other reaction, but instead I'm going to put my OH off of the least substituted carbon. Again, a regioselective reaction that prefers the least substituted carbon, Antimarkovnikov addition. In this case, I do not form a chiral center. This primary carbon has an alcohol, 2 hydrogens, and this big carbon group. Those are not 4 different groups, right? We have 2 hydrogens. So this is not a chiral center. It does not need wedges and dashes. Now I save the most exciting for last, this H₂O and H₂SO₄. This reaction goes through a carbocation intermediate, and we will follow the exact same procedure that we did earlier for finding, for seeing how and if this rearranges. So let us do that. It's a Markovnikov reaction, so we'll put a positive charge on the most substituted of the 2 carbons. Again, we have between the secondary and primary here. We'll put it on that secondary carbon. This carbocation is secondary. Let's look at its immediate neighbors. To the left, we have a primary carbon. To the right, we have a quaternary carbon. And so this can and will rearrange. We can take a methyl group and move that methyl group to the secondary position. So now my methyl group is in that secondary position, and I can put a positive charge off of the place that lost those electrons when that methyl group moved. We go from a secondary carbocation to a tertiary carbocation. So yes, indeed, we have a rearrangement. And again, we'll never have positive charges in our products, at least for now. So we'll add the OH off of this OH piece off of our tertiary carbon. And I'll keep the coloring consistent. Let's make this green. Now you might notice that this top one was probably not as intuitive to guess, right? So I would always suggest drawing out your carbocation so that you can see if it does rearrangement and how. One last question we should always ask ourselves at the end of these products: did we form any chiral centers? There are no new chiral centers in this product, right? And as a consequence, we don't have to consider drawing in wedges and dashes. So we're making really good progress. Let's start with this next reaction. It is called the Hydrogen Formation. And this Halohydrin formation involves typically Br2, or we can just say X2. And water or alcohol, we'll just say HOR here, but water or alcohol will be sufficient. And this halohydrin formation does, again, very predictable product because of the mechanism. The first thing is we're going to add, well, you probably can guess, we're going to add Br and OH. So add Br and OH, or OR, depending on the mechanism. So this first one will add OH. This next one will add OR. In fact, all we're doing, if you notice, is we'll get rid of one of the hydrogens. HOH, we can get rid of one of the hydrogens, and that's what we're adding. The next thing is we are going to do a anti-addition. So we end up forming the bromonium intermediate again in this reaction, and that bromonium intermediate is going to be broken apart. But in this case, we have two different things we're adding. We're adding a bromine and an OR. So it does probably going to matter which side we're going to add our BR versus our OR. In this case, we'll add our OR to the most substituted side. So let's take this for example. Also notice, notice that in this case I put the BR above the arrow. In this case I put the BR below the arrow. It does not matter. In fact, you could put even something like this, where I have the BR, comma, HOR. I could have had HOR, comma, BR. It doesn't matter. So don't stress yourself out about the order of the reactants, unless they have 1 and 2. In that case, it does matter. But if the steps aren't given to you, you don't have to stress yourself out about it. So what do? Well, we add BR and OR, where OR is on the most substituted side. So we have a tertiary part of our alkene. We have a primary part of our alkene. We're going to add the OR on the tertiary part. So in this case, this is OH. Again, all I'm doing is removing one of those hydrogens. Maybe I should just cross out the 2. Removing one of those hydrogens. So OH. And then I have BR coming off the other carbon. The question is, are either one of those carbons, because these are the carbons we've added things off of, or either one of these chiral? The right one, I hope you all can immediately see this one's not chiral because it has 2 hydrogens. The left one might be a bit trickier, but again, our process was when we have these rings, we'll look at the 2 things that are very obviously different. These 2 groups are very obviously different groups. You can cross out those groups and pretend they don't exist and ask yourself, do they have a plane of symmetry? This does have a plane of symmetry, meaning these are the 2 of the identical groups. These are not chiral. So neither one of our chiral centers, you do not have to indicate wedges or dashes. Let's do this process again. And this time we're going to add O and R on the more substituted side. So literally all I've done was I removed the hydrogen and simply installed this OR group on the most substituted carbon. I also have that bromine on the least substituted carbon. Now, I do want to explicitly mention anti here. So maybe I will erase this, and maybe we can draw another molecule that will force us to draw the anti-products. So let us, or at least force us to show their anti-configuration. Let's do something like this. Well, first of all, let us notice, maybe I'll delete one of these. Actually, no, we can keep it. No, we'll delete it. First of all, what we'll notice is that this is a tertiary carbon. This is a secondary carbon, so the OR group is going to be added to the tertiary side. Let's do this. O, and then that ethyl group added to the tertiary side. The BR added to the least substituted side. And then we now can ask ourselves, are these things chiral? This center here indeed is chiral. This center here is chiral. And so these are going to do an anti-addition, right? These will do an anti-addition, meaning that both of these carbons, and I will delete all of this, delete all of this. One of the groups, OR, for example, should be on a wedge, and BR, for example, should be on a dash. And then let's not forget that methyl group. Right, so this is anti. My OR group and my BR group are on two opposite sides of the molecule. This is my anti-addition. And again, I arbitrarily chose the ethoxy group to be on the wedge. I could have also have gotten the enantiomer. The bottom one, we can find this reaction is called arsine dihydroxylation. Also, sometimes you just hear it called dihydroxylation. It is adding, well, two hydroxyl, two OH groups off of our double bond. And so this has the reagents that are shown over there. We have 1 osmium tetroxide and 2 NaHSO₃. And in this case, we're going to add 2, is a dihydroxylation. We're adding 2 OHs. It's syn, so we're going to add them syn to each other. And it doesn't matter which side is more, we won't have carbocation rearrangement, things of this nature. So these are the only 2 bullet points I think are useful here. And let us add these syn to each other. So we can draw this. And again, if you want to get in the practice of just always drawing the syn product, maybe I've been using the wedges a lot. Let's use dashes. We have OH and OH. These shows that those 2 OHs are added syn off of that double bond. I could have chosen 2 wedges, but we'll spice things up. Now, this product, we did put the wedges and dashes. Let's see if we actually need them using the chiral center practice. So this carbon here indeed is chiral. It has a hydroxyl group. It has a hydrogen. It has this group over here, this group over here. So again, the hydroxyl group, the hydrogen, and those 4 groups, all 4 of them are different. And so this is a chiral center. It can keep its wedge and dash. Is this one a chiral center? Well, no. This one has a hydroxyl group and this group over here, so the hydroxyl group and that group over there. But it also has 2 hydrogens, and those 2 hydrogens are the same. So we will not consider that chiral. So technically, you don't need to indicate wedges and dashes here. You can simply leave this one on a line. We arbitrarily chose to put this OH on a dash, but we could have put it on a wedge, right? It didn't matter. So we get it's an enantiomer. For the bottom reaction, we have osmium tetroxide, so we know that this is going to be arsine dihydroxylation. And so we'll have our structure. Again, the OHs are on the same side. maybe we'll do the, I was about to do the dashes, but let's do the wedges again. So we have OH and OH. Again, it doesn't matter that I chose the wedges versus the dashes, as long as they're on the same side, as long as they're both wedges or both dashes. And then we can ask ourselves if they're chiral centers. They are both chiral centers, so we can leave their wedges and dashes. But again, we arbitrarily assign them as both wedges, so we could have also arbitrarily assigned them as both dashes. And we get the enantiomers for this product. Finally, everyone's favorite reaction, ozonolysis. Ozonolysis is going to be when there are fancy words that we can use. Like, for example, a lot of times you'll hear chemistry professors say cleave the double bond. Let's make it even simpler. We're going to cut our double bond and place oxygens at end where we cut. Now, that description might not make much sense right now, but hopefully it will after you see an example. So notice again, we have a double bond, and recently what reactions we've been doing is adding two groups off of those double bonds. Instead, what we'll do here is not add two groups off of those double bonds, but we'll simply cleave or cut our double bond. So take your double bond and literally pretend you have a pair of molecular scissors and cut them. Like, you can pretend you have some scissors and you cut them. You can just cut that double bond. What will the product of me cutting that double bond look like? Well, it would look something like this, right? Where, and maybe we can make this green, where this is the green part and this is the blue part. I'm simply cutting that double bond. Where I cut that double bond, I will place oxygens in between. And these are the products. That's it. That's all. Don't overthink this reaction at all. This is all we'll do for this reaction. This is ozonolysis. Now it could be put in a ring, like this case. But again, do not think about, is it in a ring? Is it outside of a ring? Just follow the procedure as given. The procedure says that we're going to cut our double bond and place oxygens at ends where we cut. So this is me cutting the double bond. Right, so I've cut my double bond. If you want to make sure you've kept your carbons, you can count them. So 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. And I have oxygens where I did that cut. You might also be compelled to unravel that molecule. So 1, 2, 3, 4. Always number your carbons. I've taught this course for so long, and many students oftentimes hate numbering their carbons. So number your carbons. 1, 2, 3, 4, 5, 6, 7, 8. And they lose such small points because they don't number, so make sure you number them. But yeah, if you'd like to unravel this, you can. Most professors are okay with you leaving them, however, like this. So feel free to do whatever method you choose. Finally, let us cut that double bond. When we cut that double bond, in this case, what do we end up with? Well, we end up with a structure that looks like this. Oxygen, oxygen, and those 2 carbons off of there. Let's make sure that we've, oh, also sometimes you'll see professors, they don't like to leave that carbon, a carbonyl aldehyde that is without a hydrogen, so sometimes they'll draw on the hydrogen. So make sure you're aware of that. But this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. This is the structure, and if you'd like to linearize this, feel free to do that. So we're back at the reaction web as promised. Let us do these reactions. So let's start off with everyone's favorite, H2PD, and we maybe can go our way clockwise. So H2PD is going to add H, and H is going to add them syn. So H plus H is going to add them syn. And so we can end up adding, this is the methyl group, we can end up adding H, we can end up adding H. We don't have to draw in carbon-hydrogen bonds, so you don't have to, you can draw them in if you want to, but we don't have to. We added that H and H on dashes just now, but we could have also added that H and H on wedges, so we get the enantiomer. HBr adds HBr in a Markovnikov addition. So we have H plus Br. We can do this Markovnikov. This allows for rearrangement, and this gives both the syn and the anti addition. Syn and anti addition. So what will this product look like? Well, we can end up having our bromine is going to go on the more substituted carbon. Again, this is our tertiary carbon versus our secondary carbon. We'll put our bromine on the tertiary carbon. We should also have checked for rearrangement, right? Because we could do rearrangement. I can see that this can't do rearrangement, but as you're practicing, you can always draw out, and you should always draw out, the carbocation in the most substituted position. That carbocation in the most substituted position has is tertiary, and it cannot rearrange because there is no, all of its neighbors, secondary, primary, secondary, are too low in substitution in order for it to do rearrangement. So this will not do carbocation rearrangement. No rearrangement here. Just because it can do rearrangement doesn't mean it will. Let's add, so I got ahead of myself. Let's go ahead and now add Br off of the most substituted position. Did we form a chiral center? Well, no, we didn't form a chiral center, right? Notice that these are the 2 carbons that we need to check. Both of those 2 carbons are a chiral. So we can leave our product like this. For the purple, we can see we have HBr and a peroxide. We also usually have heat or light, and let's just put light for right now to do the radical initiation. And this reaction is going to place the bromine on the less substituted side. So earlier we placed the bromine on the tertiary side. Now we can place bromine on the secondary side. And so we end up getting this. This reaction does not do rearrangement. So I should write, we have H plus Br, Antimarkovnikov, no rearrangement. And we have both syn and anti. And again, this is the Antimarkovnikov addition. Notice that we did form chiral centers, right? So this has 4 different groups. This carbon also has 4 different groups. And so what does that mean? Well, that means that we could we need to indicate stereochemistry off of both of those carbons. So this carbon, let's just assign that bromine on a wedge, and we can get either the syn or the anti. So let's start off with syn. If we have the Br added on a wedge, that means that the hydrogen that was added here should also be on the wedge, because remember we had to add a hydrogen and we didn't draw it in, but we did add it. And we ended up with putting that on a dash. So this is one of the syn products, but we could have also gotten another syn product, right? We could have gotten the enantiomer to that. In addition to getting the enantiomer for this product, we could have also, these are just the syn additions. We could have also did the anti additions, right? So we could have had the Br on the wedge, but instead of the hydrogen also being on the wedge, we could have the hydrogen on the dash, right? So we have that. And again, I arbitrarily chose to put the Br on the wedge and the hydrogen on the dash. I could have also formed the enantiomer. So in this case, we get 4 different products, right? So there's 4 different products that are isolated from this reaction. Let us erase our fun note here, so we can have more room for the real chemistry. This green reaction is one of 3 of our hydration reagents. Remember that these 3 over here are our hydration reagents. The green, purple, and blue ones that are closest to my bracket here, which means they all add H and OH. So let's look at this green one here. What is the difference between their H and OH? Well, this one is a Markovnikov addition of H and OH, but it does so without undergoing rearrangement. And we end up getting the anti product. So if we drew the product of this reaction, we're going to place our OH in the Markovnikov position. And notice that our OH in this Markovnikov position, neither one of the carbons that we have, neither one of the carbons of our double bond are chiral, so we don't have to indicate wedges and dashes. We can leave it just like this. This purple reaction also, again, is a hydration reagent, so it also adds H and OH, but it does so in a anti-Markovnikov style. This does no rearrangement, which is, again, should be a bit obvious for the all anti-Markovnikov reactions want to rearrangement. And this is a syn addition. So in this case, I end up adding my OH off of the least substituted carbon, and my methyl group on the most, my hydrogen off of the more substituted carbon, but I don't have to draw in that hydrogen. You can draw it in if you want to, but you don't have to. The 2 carbons where we added our substituents, this carbon and this carbon, are they chiral? They both are chiral. They both have 4 different groups. Because they both have 4 different groups, we need to consider, we need to add wedges and dashes. And our wedges and dashes must be so, in this case, that the 2 groups that we've added are syn. So that means that this OH is on a wedge, and this hydrogen is on a wedge. If that's the case, well, that means that this methyl group is on a dash. I don't have to draw in bonds to hydrogen, so I can erase this. And even though we get this. Now, even though the methyl group and the OH are anti each other, the OH and the hydrogen are syn. That's implied by this structure. And I didn't have to arbitrarily choose to put the OH and the hydrogen on wedges. I could have put the OH and the hydrogen on dashes, so I get the enantiomer. Now notice the difference between this reaction and this reaction. in terms of stereochemistry. This Antimarkovnikov addition of H and Br, notice that we have 1, 2, 3, 4 products. In this case, we only have 1, 2 products. Why is that the case? Well, they both had 2 chiral centers. But for this top reaction, the stereochemistry did not matter. It was non-stereoselective. However, in this case, it was stereoselective. We had to do a syn addition. Only the OH and the hydrogen had to be on the same side of the molecule. That is, we cannot draw a case where the OH and the hydrogen are anti each other, because these are not the conditions of our reaction. These are not the restrictions that we were asked to follow. So this is not a product that we'd yield if we do this reaction in a lab. Finally, we get to this next reaction, our last hydration reaction. H plus OH is a Markovnikov addition that does rearrange, and it has syn and anti. Let's check if it can do rearrangement by placing a positive charge on the most substituted carbon, so in that tertiary position. And that tertiary, let's zoom in a bit. That tertiary position is next to a primary position, which is next to a secondary position, which is next to a secondary position. None of these positions have a better substitution than our current, so we will not do a shift. We'll erase that. Okay, so this is going to end up adding our OH off of the more substituted carbon, and then doing our analysis of stereochemistry, we'll find that again we formed no new chiral centers. In fact, we ended up with the exact same product as we did for this particular reaction, these 2 Markovnikov hydration reagents. Okay, so now let's get to our ozonolysis reaction. This is when we cut our carbon-carbon double bond. So this one's the only one that's really different from the rest of our addition reactions. We'll cut our double bond. When we do that, what do we have? Well, pretend we have a piece of molecular scissors and we cut that double bond. That's all you should think about doing. And then wedge oxygens where you've had that cut. And this is it. This is the product. This is done. Reaction over. Osmium tetroxide. This is our dihydroxylation reaction, and we can add 2 OH's syn to each other in this case. So this reaction allows us to add OH and OH, and they are syn to each other. So we end up, let's just put the OH's on the same side of the molecule, indicated by these dashes, and that methyl group we should still have. Again, I randomly chose to put the OH's on dashes, so I could have gotten the enantiomer as well, where both the OH's are on wedges. This next reaction is going to allow us to add chlorine and OH, where we add OH on the more substituted side. And the groups are going to be added anti. So when we draw this, I end up with the OH on the more substituted side, which is this tertiary side. So I can put my OH here. And because my other group is chlorine and is added anti, I'll draw it like this. Again, I chose the OH to be on the wedge randomly and the chlorine to be on the dash randomly, but I can get the enantiomer and get the same product. And this is the answer for this one. And chlorine, this one's even easier. Instead of me adding chlorine and OH, this one is chlorine and just chlorine. It doesn't matter which is on the more substituted side, and this is an anti-addition because of the chloronium intermediate that we form. So in this case, all I have to do is I draw one chlorine off of one carbon on a wedge, the other chlorine on a dash, and I can get it's an enantiomer.